In the previous module, we have looked at the imperfect information extensive form games, and we have also discussed that this is actually a richer representation than both the perfect information extensive form games and of course normal form games. Now, with this richness in its representation, its strategy sets should also be increased, or the strategies in general should be more richer. So the strategy set for player I, we have already defined it. That is a Cartesian product of all the set of actions that are available at every information set for that player. Right? These are the set of all pure strategies. Now, in this imperfect information extensive form game, we'll also have to talk about the randomization over these strategies. This randomization was not necessary in the context of perfect information extensive form game, because we knew that the pure strategy Nash equilibrium definitely exists in the perfect information game. Why is that? Because the subgame perfect Nash equilibrium for any finite perfect information extensive form game always exists, and a subgame perfect Nash equilibrium is also a pure strategy Nash equilibrium. So we really never bothered about randomization. But in the context of imperfect information, the players may not see the moves that has been made by the other players. Just think about the previous representation of the normal form game, the neighboring kingdoms dilemma. In that case, we know that it is possible to represent this normal form games into extensive form games using this imperfect information setting, and there are certain normal form games for which you do not have perfect information pure strategy Nash equilibrium. So very naturally we cannot find a pure strategy Nash equilibrium in the IIEFGs. So we'll have to talk about the randomized strategies. So let us look at how we can do that. Now, in the context of normal form games, these mixed strategies are just randomizing over pure strategies. Right? That is the way we have defined mixed strategies. Now, extensive form games, randomization can happen in two different ways. So one way is that you first list down all the possible pure strategies at the very beginning of the game. That is the way we have defined the strategy in an extensive form game, even for the perfect information setting. Now, once you have defined those strategies, you are talking about randomization, some probability distribution over all such strategies for a player. Now, the other way of randomizing is over the action at a given information set. Okay, and this particular way of defining the randomized strategy is what is called the behavioral strategy. Let us take a look at one example to understand this point of behavioral strategy. So let us look at this game on the left. So player 1 is first playing here, then player 2 takes its move. If player 1 takes L1, then the game ends, and if it takes R1, then player 2 gets a chance to play, and it can pick two actions here, and then it is player 1's turn again. And now this is an information set. So when player 2 is making a move, player 1 does not know which move player 2 makes. You can think of that if player 1 is making this move R1, they run into a simultaneous move game where 1 and 2 has to pick their strategies simultaneously, and that can be represented using this normal form, this extensive form representation. Now, given this, notice that because these two nodes here and here are falling in the same information set of player 1, which is represented by I1 superscript 2. So I1 superscript 1 was the first information set, which was a singleton. So here you have two elements here, and the actions that are available at every node, every history of that information set are identical, L2 and R2. Right? So now you can think of two different ways of randomized policies. You can first list down all the possible strategies. Right? So player 1, so here we are just looking at player 1. So it can have these four possible strategies. You can think of a probability distribution over this four strategies of player 1. So that will be given by sigma 1, L1, L2, and so on. Also, you can think of a strategy which is just randomizing whenever you are at a particular information set. Let's say when player 1 is at the origin, the very beginning, it tosses a coin and chooses L1 or R1. Similarly, when it comes to this information set here, it cannot distinguish which of this history that player 1 is in, but it can still randomize independently the same coin or maybe a different coin again and choose L2 or R2 accordingly. So this is different from this mixed strategy here, right? So the mixed strategy is first listing down the complete contingency plan and then randomizing over those different possible plans. But in the other kind of strategy, which we are going to call the behavioral strategies, the player is randomizing at every information set. So at information set IE11, L1 and R1 are the two strategies, and the behavioral strategy for player 1 at that information set, we are going to say that is a probability distribution over this L1 and R1. So remember, we use this notation delta of a set to denote the probability distribution over that set. Similarly, the behavioral strategy at the other information set for player 1 is a probability distribution over L2 and R2. So this is something which is fundamentally different, and if you think about it carefully, in sequential movement, sequential interaction of players, behavioral strategy looks more natural because that's the way people typically pick their actions. So let us make this definition formal. So the behavioral strategy of a player in an imperfect information extensive form game is a function that maps each of her information sets to a probability distribution over the set of possible actions at that information set. So if you go over this slowly, you can understand that this is exactly what it is meaning, that the actions that are available at that information set, I11, the behavioral strategy is just at that information set is a probability distribution over that possible actions. Now the very natural question is, what is the relationship between this mixed and behavioral strategies? We have defined two ideas. So in this case, in this example at least, we can see that these mixed strategies are living in R to the 4, because there are 4 different strategy for player 1. So everywhere we are talking about player 1. So for player 2 it is very simple because player 2 is only playing once, and its information set is a singleton. Therefore the mixed strategy and the behavioral strategy are identical in this case. So for player 1 we can see that these mixed strategies are living in R to the 4, whereas the behavioral strategies are living in 2 R to the 2 spaces. So clearly we have a smaller number of variables that we can deal with, and also with this assumption of independence that at every information set, and this is a crucial point, that at every information set, this player is picking its behavioral strategy independently. That is important. Right? So in some sense, you can think of that these mixed strategies are more richer in some sense, or a larger concept. We'll see how we can actually justify or contradict that statement. Now the question is, can a player, so if you have a richer or a larger concept, then it is also very likely that a higher payoff may be achievable in one type of strategies than the other. Or maybe we can have an equivalence. So whenever you have a mixed strategy in an incomplete information extensive form game, maybe you can also have a equivalent behavioral strategy. So how can we define equivalence in that context? So the equivalence will be defined in terms of the probability of reaching a vertex. So these are all random choices, right? So you can pick one node, maybe a terminal node or a non-terminal node, and ask about the question that what is the probability if you pick a specific strategy profile, a mixed strategy profile, or a behavioral strategy profile, what is the probability of reaching that node? So we are going to denote that using the following notation. We will denote row, comma the node that you are. So it takes two arguments. One is the node that you are looking at, the history if you want, and the other one is the strategy. So it could be a mixed strategy, it could be a behavioral strategy. So this notation is actually denoting what is the probability of reaching that node X under the mixed strategy. So if you are talking about mixed strategy, then that is the mixed strategy profile. If you are talking about the behavioral strategy, then that is the probability of reaching X under the behavioral strategy profile B. And of course, this B is actually BI, B minus I. In particular, you can mix. So one player can play behavioral strategy, the other player can play mixed strategy. That is also possible. So let us look at an example to understand this point. So let us look at the same example, the same game tree. Now, if we pick this point to be this node X, and we ask the question, what is the probability that you reach this node X under the mixed strategy profile sigma? And that is going to be the probability with which you play R1, right? And multiplied by the probability with which, the probability with which player 1 plays R1 and the probability with which player 2 plays R, lowercase r, right? That is what is written here. Now we know that this is a probability, and the way you can find out probability with respect to one variable is by marginalizing over the other variable, right? So all that we have currently, the representation of the mixed strategy is over the entire strategy space. The strategy are R1, L2, R1, R2, and so on. So we know the numbers here. So from that we can actually compute what is the probability that player 1 is playing the strategy R1. In particular, it is just summing over all this other probabilities, marginalizing over this the other action, the action that player 1 can play in the next round, in the second round. And for player 2, it is simple because there are only two strategies in its strategy space, either L or R, and then we can use it directly. So that is the probability that you can get for reaching this node here under this mixed strategy profile. Now for the behavioral strategy, it is actually simpler. The player 1 and player 2 are independently randomizing at every information set. So I can just ask the question that at this information set, at the very beginning, what is the probability that player 1 will pick R1? And then we can ask the similar question, what is the probability at this information set for player 2 that player 2 will pick R? And those are given by these numbers respectively. And if we take because all these picks are independent, we can just take the probability, the product of these two probabilities, and that is going to give the probability that we reach this node X under this behavioral strategy profile of B. So that is the explanation of this term. Now we should keep in mind, which I just mentioned, that different players can actually choose different kind of strategies. So in particular, player 1 can pick sigma 1. So let's say player 1 is choosing a mixed strategy and player 2 is choosing a behavioral strategy. Then what can happen? Then we can equivalently represent that. There is no harm in overloading this notation. So what is the probability of reaching this this node X, when player 1 is playing this mixed strategy and player 2 is playing the behavioral strategy, you can multiply the corresponding probability of player 1 playing R1 and player 2 is playing lowercase r. Now we are in the right position to talk about equivalence. We said that the equivalence are in terms of the probabilities. So we will say that a mixed strategy sigma I and a behavioral strategy bi of a player I in an imperfect information extensive form game are equivalent if every mixed or behavioral strategy vector of the other players, that is because it can stand for both mixed or behavioral strategy. We have denoted this with a different notation, xi of -i. So if for every such strategy vector of the other players, it can be either mixed or behavioral, and at every vertex x of this game tree, this probability equivalence should hold. So you should get the same probability of reaching a particular node by playing sigma I as well as bi, when other players can either pick a mixed strategy or a behavioral strategy. If that holds, then we can say that this mixed strategy and the behavioral strategy, these are equivalent. So just to give you an example, and I leave it to you for verification, you can see that if you are given a mixed strategy of sigma 1 for player 1, this b1 of ii1 at l1 will be the equivalent behavioral strategy for this mixed strategy is going to be this what is written on the left hand side. Similarly, the R1, and you can also see what is the L2, and it is going to be the conditional probability. Given that player 1 has played R1 in the first round, what is the probability that it plays L2 in the second round? That is going to be the behavioral strategy for player 1 in the second information set. This should actually be, the subscript will be 1 and the superscript will be 2, because this is the second information set for player 1. So if this happens, then we can say that this b1 and sigma 1 are equivalent. That is, you can find at every node here the probability of reaching that node under this behavioral strategy as well as in the mixed strategy are same. Now these equivalent strategies are actually inducing the probability of reaching a vertex. So we can actually say something more about these equivalent strategies. The equivalence, of course, by definition holds at the leaf nodes too. Right? So because it has to hold for every node, it should hold even for the leaf node. Now what we claim is that it is enough to check the equivalence only at the leaf nodes. And why is that true? If you pick any arbitrary non-leaf node, then the probability of reaching that node is actually going to be equal to the sum of the probabilities of reaching the leaf node in its subtree. So the game should end at some leaf node. Therefore, if you add up all the leaf nodes in certain subtree of a node which is non-terminal node, then you will get that probability of reaching that particular node. So therefore, if you have already ensured that the equivalence holds at all the leaf nodes, then you are actually done. You don't have to verify that in other non-terminal nodes. It is going to be the same. Now probabilities are kind of something fundamental. The game is not changing. The game tree and the utilities, the pure utilities, are going to be the same. So therefore we can actually extend this equivalence of the mixed and the behavioral strategies even for the even in the context of utilities. So if you have two strategies, sigma I, which is a mixed strategy, bi, which is a behavioral strategy for player I, then you can also say something about the utility equivalence. So so this is important for every mixed or behavioral strategy vector of the other players. So here we have only focused on player I, and they have equivalent mixed and behavioral strategies. Then if you look at any other strategy, it can be mixed or behavioral, of the other players, then what you can say is that the utility for all the agents at these two strategy profiles, where player I is picking the mixed strategy profile, other players are picking what they are picking, and player I is picking the behavioral strategy, the other players are picking the same mixed or behavioral strategy profiles. And notice that this is true for all j in n. Of course, this also holds for player I, but it also holds for the other players as well. Now you can repeat this argument for any equivalent mixed and behavioral strategy profiles, and what you can get is that you can show, this is a simple corollary of the previous result, that if you have two strategy profiles which are equivalent, which means that for every player this sigma I and bi are equivalent, then the utilities are going to be the same for all these players in this game.